All right. Hey, everyone. I'm Rob May. I'm the CEO of Neurometric.
And I'm Calvin Cooper, COO at Neurometric. We're co-founders, and this is Inference Time Tactics, a podcast for builders, researchers, and engineers who want to understand what's happening in this next era of AI.
So we're excited for our guest today. We're joined by Pawan Deshpande, who I've known for quite some time. He's an AI researcher, engineer, founder, angel investor. He's been in a bunch of good companies that you've heard of, Anthropic, Toast, which is not an AI company, but a very famous Boston startup company. And his career spans from research at MIT, research at Google. He founded a content marketing startup called Curata, and then has built products at scale and at Domino Data Lab. So Pawan, before we dive in, do you want to give a little bit more context on, sort of your background and particularly how it relates to inference?
Sure. Yeah. So thanks for having me on here, first of all. So I started off from a technical background, went to MIT for undergrad and grad school back in the day. And that's where I got exposed to machine learning. This is in the pre-deep learning era. And what I focused on in graduate school was decoding, which is now known as inference time compute. Essentially, after you've trained a model, how do you get the best possible output? And then I also continued that when I was at Google as well. I built their core machine transliteration model, which is still in use today. And so there's a lot of exposure to that as well. And then a lot of those techniques were then carried over into my startup as well. So I think a lot of what we'll be talking about is the stuff I worked on 20 years ago now. But I think there's a lot of learnings for how to approach inference today. And then a lot of things are different as well.
Awesome. Thanks again for joining us. We're really excited to dive in. And so as we start this first segment, how about we zoom out and talk a little bit about your overall thoughts on model training versus inference?
Yeah, sure. So I think inference, the way I define it is finding the best output for a model, given that you've trained it. So given that it has the right architecture and it has the weights have all been set, how do you find the best possible output? And the thing is, if you have a model that doesn't have adequate knowledge or doesn't have the right representation of that knowledge, even if you have the best decoding, you're not going to get a very good output. And this could happen because the model doesn't have sufficient training data. It could have the wrong architecture, or sometimes something else about the model training is off. It could have the wrong kind of loss function or hyperparameters during the training. And so that's one way to think about it. So you really need to get your model training right. The other side is, let's invert that. Let's say we have the perfect model. It has all that training data we'll ever need in the world. It has large enough vocabulary. It has diversity in that training data. It has the best and very rich model architecture. And you've thrown a lot of compute at it sufficiently so. And even if you have all that, if you have a poor inference technique, you're not going to get a very good output. So you really need both of those. And I think in recent years, there's been a ton of focus on the model training side. And now the biggest gains are going to happen on the inference side.
When you talk about the inference side, in reviewing some of your work, one of the papers you wrote was about randomized decoding. And I'm really interested. Is this what you found, that sort of randomization worked better than any kind of structured algorithm?
Well, the thing is, what does better mean? And so there's always this trade-off of, are you optimizing for the best quality output, or are you optimizing for compute time? And it's a balance between the two. So that paper, it kind of did this approach where we took three very different approaches towards doing this. And kind of the middle of the road approach was a randomized algorithm. So in short, what we're doing is we did one approach, which did integer linear programming, which is basically finding the best possible output. And sometimes that would take like 136 hours of compute time to figure that out. On the other side, we're doing greedy search or beam search, which is extremely quick, but resulted in a very poor quality output. And then this randomized approach was right in the middle. And that's because by randomizing it, we're able to leverage parallelized computation. So we could try more than one solution simultaneously and arrive at a pretty good answer very quickly.
And was this on a specific type of model? Were these neural networks or SVMs or something else, or was it a broad swath of different model types?
Yeah, this is like pre-deep learning era.
Okay.
This was basically we're doing a graph construction. So it was a class of problems that we deemed as selection and ordering problems. So if you think about it, this encapsulates a lot of natural language generation. So if you are producing a multi-document summary, you have multiple documents, you're taking out sentences from each, and you're constructing a new document out of there. Or you're generating a new sentence. So you take a document and you're like creating a sentence out there. Those are selection and ordering problems. The selection comes from picking the right words to represent in that summary that you're creating, and the ordering is in what order you put them. So it's like a joint optimization problem where you're optimizing for both the selection, the right words, and then the ordering of those words. And if you think about it, that's kind of like how LLMs work, although LLMs have a more continuous probability distribution as opposed to discretized ones. But that's kind of the class that we're working on. So it wasn't the complex neural architectures we have today, but it resembled that in many regards.
So double clicking on that. That was like, what, 2007 when you wrote the paper?
Yeah, 2006, 2007, around then. Yeah.
Yeah. What about that paper still applies today, and what's different now?
Yeah. Well, I think, people still use beam search. I mean, that's like how LMs do a lot of decoding these days. A lot of them just use greedy decoding. So you have a beam of size 1. And so you're getting answers very quickly that way. So this quality versus speed trade-off, that still very much applies. And then another challenge that I think still applies is on the eval side. There's a lot of talk about LM evals. I was previously at Galileo, which is a LM eval startup. And back then we used to use Rouge scores. So you're, I guess in simplistic terms, looking at overlap between the ideal output in your eval set and what you're generating. And that's a very crude way of doing evals, but people kind of still use some of those techniques today as well. And there's no like really perfected way today of knowing if your LM is producing a great answer. This LM is judges, there's a lot of things like that, but that's still something that people are trying to figure out.
Yeah, it's definitely something we've seen when you look at the AI landscape more broadly, like stepping back from inference, and you think about why there hasn't been more adoption of agents and all this kind of stuff. A lot of the problem is the fact that as you're building agents to do these more complex tasks, there's no good evaluation data set to tell you if the agent works well or not. And sometimes it's even hard. Like if you're having an agent write a report, I mean, I don't know what you would do other than like edit the report and give it back to the agent the way you would do it if it was like an employee, right? So the more complex these tasks get, I think that's going to be a common problem that's going to probably hold AI back until people just come to terms with the fact that like you have to teach these machines this way, maybe, or somebody finds a way to integrate everything that we do into some kind of machine coded workflow.
Yeah, and I think agents are more useful when they're doing more complex tasks, but it's also harder to verify them when they're doing more complex tasks, and they're more likely to make mistakes the more complex they are. So that whole thing just makes things very, very hard.
Yeah. So let's move on to some of the work that you did at Google, working on their machines transliteration, and how that applies to both like training and decoding.
So I was working on machine transliteration, which a lot of people confuse for machine translation, which is more popular. So transliteration is where you are writing a word, but you're writing it in a different script altogether, not the language or character set that it's normally written in. So where this applies is if you look at India, this is, back around, it's 2005 now. This is kind of pre-smartphone era. People in India, they used to own normal like English character keyboards, but when they would write in their native languages, they would use English characters to phoneticize it out. And so that works, but it's like a lossy way of doing things, and they're not actually communicating in their like native scripts. And so what we're trying to do is to build a machine learning model where you can type in like my name, Pawan, Pawan. You could type that in, it'll automatically show up in any Indian language script. And so that's the machine learning setup. So you have an input on one side, and then your output is in the native script. So the first thing there was getting enough training data. It was really hard to like find training data for this problem. And so what I found online was actually Bollywood song lyrics were like a great place for this, because there's like thousands of those online. This is like 20 years ago now, but people had written them both in the native script and in like the English transliterated version. So I wrote a crawler to go index all this data and then build a parallel corpora, and then wrote my own model that's kind of based off of hidden Markov models to train against them. So with that, I was able to get like basically a model that you could then type in, in English characters, whatever you're trying to phoneticize out, it'll show up in an Indian script. And it would, for a single word, it would generate like hundreds of possible variations. So this is the decoding piece. The problem though is that a lot of those were like invalid words. They actually weren't words that people would say. There were a lot of wrong answers in there. And so on the decoding side, another thing that I was able to do, because this was Google had indexed the entire web. And so they had a language model of every, like, for example, Hindi word out there in the world. And so you can then filter it through there and look at occurrence frequencies and then bump up the most kind of common phoneticization of a word. And so that like bumped the quality score from like 60% to like, 95% plus. And so that's an example of where both training data was important, but then also the way that you do inference at the end. And so you really need both of those for this to work.
It's really cool. And I can imagine that got massive adoption in the real world. Speaking of adoption, what's really holding back adoption of agents and in the real world, especially on the enterprise?
Yeah, well, I think it's what we're touching upon earlier is that it's really hard, one, to just debug them, but even before you get there, verify that it's doing the right thing. So I think there's like 4 things you need to really verify things. One is it has to be cheap to verify. 2 is to the extent that a machine can verify it versus a human, the more likely it is that you'll get there. You need like some sort of scoring and reward function to know if you're heading in the right direction as an agent kind of like comes up with answers. And then the 4th thing, this is a computer science term, but idempotency, which means that you can run something over and over again without any side effects. And so if you look at this, I think we have seen agents really take off for coding. And that's because coding meets all 4 of these. Coding, first of all, it's cheap to verify. You can just run the code and see if it works. So if Cursor generates something, it runs it, makes sure it works or it doesn't. It's machine verifiable because the computer can just run it. And you have this implicit reward function where you could see how much of the unit test does it pass or does it actually execute. And then you don't have to worry about side effects because it's running in a sandboxed environment. Whereas if you look at, I know a lot of people are doing AI agents for travel booking. Travel booking like almost has none of those. It's hard to verify. There are a lot of side effects if I go book a flight or like, and the human really has to verify it at the end of the day. There's not an obvious reward function for that as well. So I think as we get to more human-centric and business use cases, a lot of those attributes of how you verify break down. And that's why I think agents are not coming to life in some of those problem spaces. So
one of the things that's different probably from when you did your original work on inference is the models are so much bigger. And I don't know that a lot of people who aren't technical realize that some of these large language models are giant when you compare them even to a program like an operating system or something like that. And ChatGPT, I think GPT-4 is like 70 times the size of Windows or something like that. So when you think about that stuff, do you think like intuition would tell you there's probably a lot of opportunity to optimize inference? And, where do you see that going? Why do you think that people haven't paid more attention to that opportunity? If it's going to happen, do you think it's going to come out of the large language labs? Do you think it's going to come out of the sort of inference companies like Fireworks and Together? Or do you think it's going to be a bunch of third-party solutions stitched together? Because it's a complex, there's multiple layers where you could optimize inference in the tech stack. And I'm just wondering if you think like somebody will peel all that off at once or it'll be a collection of parts, or what do you think is going to happen there?
Yeah. Well, I think the reason there hasn't been as much focus is the models, even if you had the best inference in the world, it's really fast and it finds the best answers, and you get both somehow magically. I think in the past, that still wouldn't have produced a good output. And now we're kind of reaching these diminishing returns with training. We have like almost all the data we can ever kind of consume for these models. That's why people are now focusing on reinforcement learning environments where we can keep generating new data. People are experimenting with new model architectures. I think we've like transformers. We're now kind of hitting this plateau with that. So people are playing with like mixture of experts or state space models. And then data centers, there's big data center build-outs, but that's also going to lead to diminishing returns on the training side. So I think now all of a sudden people are now focusing on the inference side of things because they're seeing that it costs more and more to get those incremental gains from the training side. I think in terms of how it's going to play out, and you do see innovation from like Together and the other folks on the inference side. And that's, I think, primarily on the performance side of things. So I think inference is two areas to optimize for. One is performance, and the other area is quality. I think one simplistic view is that we'll see the compute and efficiency gains come from the inference providers because that's directly tied to their business model. And we'll see the quality stuff come out from the labs who are actually building the foundational models because their differentiator against other labs is the quality of their output. So one simplistic view is that's where the innovation is going to happen based on what their businesses are optimized for.
Do you also think there's a piece of the ecosystem here? You know, at the last GTC conference, Jensen Huang got up and called inference time scaling, test time compute, whatever you want to call it, the third scaling law. And that piece, that view of it's not even really about optimization, right? It's about adding algorithms and techniques that maybe push the capabilities of models forward. And you see that with some of the reasoning algorithms, chain of thought, best of n, more complicated versions of beam search and stuff like that. Do you think that those types of tactics and techniques are going to push model scaling forward significantly in terms of their capabilities, or do you think there's significant limitations there? Seems like a large unexplored space still.
Yeah, I think there's still a lot to do. I think there may be like diminishing returns at some point, but right now there's a lot to do around parallelization, even including specifying more richer parameters in inference. So for example, having more controllable generation. So you say like generate X, but avoid, Y while maintaining this Z style. And right now you can't really do that. So you can't have like joint kind of multi-objective optimization. So there's like a whole set of things to do there. It seems like a lot of companies are focused on training. So you can do this multi-objective optimization in the training phase and get the models to behave in certain ways. But I think actually a lot of that's now going to shift over to the inference side.
Yeah, and training is so expensive, but the inference side, the barriers of entry seem to be a lot lower. So curious your thoughts on open source models and open source communities and strategies, especially in the inference time compute area.
Yeah. Well, a couple of thoughts here. So this, who's been on the open source model side? It's been largely Meta with the Llama models. Unclear where that's going today. And with their new superintelligence lab, will they continue to produce open models? Will they even have models available, or they'll just use them for internal use? I think that's a big question mark. But there are companies like Reflection AI coming up that are now focusing on their own models and putting them out there. I think it makes a lot of sense for enterprises to adopt that. What worries me from kind of a business model perspective is that once you have open weight models that are being used in the enterprise, how does that work every time a new version that is released? There'll have to be a whole process to fine tune those models and retrain the models internally and get them to align to whatever the end user's objectives are. So that's one way the world could go. The other way it could go is that enterprises just are okay with running things in the cloud, just like how a lot of businesses are okay with SaaS, and that just eventually happened. So it's kind of unclear to me where open source models are going today in terms of just having everything hosted or kind of going through and building up this whole stack in order to be able to like retrain and fine tune internally.
Yeah, it's difficult to tell. When Zuck went around offering massive salaries to recruit a lot of the best AI people, it's hard to tell if there were a lot of rumors going around Silicon Valley that they were going to move away from Llama and all that, and it could have been competitors, trying to talk down. Like you don't want to go work there; they're not going to keep working on those models or whatever. So who knows how much of it was that? I'll tell you, we've from our interactions with the Llama team, they seem very dedicated to it and want to push it forward. But Coop and I were just at the AI Infrastructure Conference in San Jose, and one of the more interesting talks was from the VP of Infrastructure at Meta, who pointed something out that I think not a lot of people realize, which is Meta is one of the few companies that has the capabilities and the incentives to optimize at almost every layer of the stack. Like they are building chips targeted towards recommendation algorithms, sort of optimized for that. They have super large graphs. They have a lot of data. They monetize it themselves too. So they're a really interesting sort of cog in the AI ecosystem because of that. Their sort of incentives and their structures and what they might want to do is so different than everybody else's.
Yeah, that's very cool. And I'm just thinking about that. If you look at I think React and GraphQL, these have nothing to do with AI, but that's front end stuff, and that came out of Meta, right? So they've been able to innovate at multiple layers.
Yeah, let's move a little bit before we wrap up into two other areas, sort of some general AI views, and maybe a little bit of your thoughts on investing in the space as well. One of the blog posts we read when we were doing our research for you was this framework that you wrote on generative AI and software on usability versus functionality. Tell us a little bit about your perspective on that.
Yeah. So I think forever now, for the past 40 years, software has always had this paradigm where software that's easy to use can't do much, and software that can do a lot is hard to use. And so a classic example is that you look at Photoshop, that experts, in graphic design use and can do anything you want. And you look at Canva, which is more for the newbie and can't do as much, but gets the job done for that persona. And so you look at this for enterprise software, CRM systems, everything always kind of straddles this axis here where, the more it can do, the more complex software it gets. I think what's happening now is generative AI all of a sudden is breaking down that paradigm where you can have like a Replit or Lovable where someone has never coded before, but they can build a very high power application in a very easy to use interface. And that's what natural language enables. At the same time, similar types of technology like Cursor can get an expert to be much more efficient. So you're actually converging on the same point where you're making it very easy to use to do a lot of very powerful things. And I think that's completely transforming software. I think how that plays out is that we still are going to have this dualism in terms of how software is developed. I think there'll be like two winners. So there'll be someone who's optimizing for the easy to use novice use case and someone optimizing for the experts. And the only difference between the two, they can almost do the same things. The difference is just the interface. So if you look at like Cursor, it's built into IDE in the existing workflow where someone can go in and intervene and see exactly what's going on. Lovable and Replit, they don't expose the code as easily, nor do they need to. But at the end of the day, they both generate code. They're probably on equal footing in terms of how powerful they are. So that's an interesting kind of observation and way that I'm thinking about at the app layer how things are playing out.
So much is changing about how you get to product market fit and build a company. So double clicking on that, what signals do you look for as an angel investor, and how should founders be thinking about the market?
Well, I think just focusing more on the technical founders, especially in the AI infra space, because I know that's a focus area for this podcast. I think there's a lot of folks who are great in lab settings, but that doesn't necessarily translate to success as a founder. And there's a whole bunch of skill sets that are required there. So, and that's where I see a lot of like failure modes, and a lot of people are investing and people are just coming straight out of lab. And that doesn't work. So I think specifically where that changes is they kind of have to get rid of this mindset that if you build it, they will come. There's more to it than just having like the best inference technique or some technical aspect to it. I think that's one. Two, being able to not just dog food it yourself and think that you're the best customer. And this is a trap. Dog fooding's a very tight feedback loop, and it's great when you can get to work, but it's also a trap too, where you overfit for yourself. And I see a lot of technical founders falling for that because they're building for themselves, and that doesn't actually represent the true market. And then the third piece are just thinking through the business model, just not saying I have this better way of doing things, but what are the business implications? How do you price it? Are you going to be competing against the big labs for this stuff? And kind of thinking through that. So those are, I think, three kind of like places where I probe for on technical founders if they're in the AI interest space specifically.
Yeah, one of the things that Cooper and I decided to do when we built out the team for Neurometric, we have two other co-founders, and it was like, I'm pretty technical, right? I used to do computer chip design and stuff like that, and we chose two guys that were much more deeply technical than me. But the thing that we all sort of have in common is we sort of lean towards systems level people, right? People that have worked at multiple layers of the stack and understand how they interact with each other. Byron, one of our co-founders, did reinforcement learning algorithms, very high level stuff, and then was like an expert CUDA programmer in the early days of CUDA. And then Dave Roshwork has done a whole bunch of like really interesting from like new silicon design. He built a $9 CPU and all the way up the stack to software. So I think it's interesting in talk. Cooper and I have both done investing and founding and still sort of do both. And it's really interesting to think about where we are in this world, because it's like, I don't know that a lot of the tactical lessons that we've learned about how to run companies are becoming irrelevant going forward. Yeah. So, I particularly building like an enterprise software company, like I don't know that the cold emailing, BDR, SDR, cold, like that stuff's getting so competitive.
Customer success is out the window now. It's forward deployed engineers. There's confusion, right? Yeah. Hey,
people used to hate consulting. Now a lot of AI companies have to do it, and you're, it's funny you mentioned the whole, the whole issue about do they think about business model and everything else, and I think you have to think about the opportunities there early on, and you have to make some, you don't know how the world's going to play out, so you have to make some bets on what the market structure might look like. But I'd be very worried that foundation model lab is just going to eat my lunch and do what I'm doing and compete with me. The tech stack pieces aren't settled, so people are going to come into each other's turf. So there's a lot of interesting stuff happening. It's a super fun and exciting place to work. I will say that.
Yeah, I was looking at a startup that does, if you look at like apartment staging, where you go and buy furniture to make it look nice. They're using generative AI, so they could remove all the furniture and then add nice furniture. So your Zillow listing or your apartment listing looks good, and they were doing really well. They ultimately got acquired by Zillow, and I think that was actually the right move, because like a year later, Nano Banana came out, and now you can just do that for free. And so just overnight, there's just startups that just kind of vanish, and they weren't even like, they're very much at the application layer space and focused on real estate, but even they weren't immune to stuff like that. So it's just crazy.
Yeah, we've seen stuff I've never seen before. Like I've seen companies like pop to tens of millions of dollars in revenue very, very quickly, and then fall back down to seven figures, single digit millions and stuff like that. It's it never would have happened in the SaaS world.
Yeah. Lensa is my favorite one. I don't know if you tried that when it came out, where you take pictures and it makes like artistic portrait of yourself. And I think they got to tens of million in revenue. Everyone downloaded the app. Early days, like of generative AI, and then there was just, it came crashing down the next month.
So where should people be building then?
Yeah, well, I feel like generative AI is the wedge to get in, but then go and build back. So, for example, there's a couple of companies that I'm invested in that are focusing on more the SMS layer as a way of customer interaction, which is now enabled with AI, so you can automate a lot of that. But if they just focus on that, that's not going to get them to be a sustainable business. They have to go and build the back of the stack. So I think like system of record is a good way of building differentiation if you can own that. So, and that's not something the foundation model companies are going to touch. So if you can go from there, from AI, and then build backward into something else that has lasting power, or something that goes under, AI infra, hardware, stuff that goes a layer lower than anything that the foundation models companies can touch.
Cool. Well, Pawan, this has been fascinating. We should have you back on somewhere down the road, and because this is a space that's changing quickly, and you got a lot of interesting perspectives. So definitely have to come back on in a couple of months. If you guys are listening and want to dig deeper into Pawan's work, we'll drop links to his thesis and his papers and things like that as blog posts in the show notes.
And if you're building in the inference stack or thinking about AI systems orchestration, please subscribe to the show. Stay tuned for future episodes. Thanks again, Pawan. Thanks everybody for tuning in to Inference Time Tactics.
Well, thanks for having me on.
Appreciate it.